Hi, my name is Jacintha and I am a final year student majoring in data science and artificial intelligence. My FYP is on network analysis on neuroimaging data and I was supervised by Prof. Kelly Kerr. This video presentation will be organized according to four parts. I will first give an introduction on what is brain network analysis, then explain the two major parts of the project, which are brain network construction and the graph convolutional network or GCN baselines. Lastly, I will suggest some future directions. Let's first understand what brain network analysis is about. The brain can be thought of as a large graph in the non-Euclidean domain, whereby the regions of interest or RIs are nodes and the connectivity between RIs are edges. As this project is limited to using diffusion tensor imaging or DTI as the mode of neuroimaging scan, structural connectivity is defined for the edges. Additionally, subject data was taken from the Alzheimer's disease neuroimaging initiative for two classes, cognitive normal and late mild cognitive impairment. Brain network analysis consists of first extracting the brain graph from the initial DTI scan, which involves multiple preprocessing steps before using modeling techniques to gain interesting insights from the generated brain graphs. There are various applications for brain network analysis. From a clinical perspective, human brains can be analyzed to aid in diagnosis, disease staging, and monitoring of response to treatment for neuropsychiatric conditions. For the computer science community, the vast graph topological properties of brain networks offer interesting insights into network science and graph theory. This makes brain network analysis a highly interesting and relevant field for research. Diving into the implementation details, we first examine the brain network construction process, also known as the DTI preprocessing pipeline. The preprocessing steps shown in this slide are a highly summarized version of the actual implementation for the purposes of presentation. The main software used for the preprocessing pipeline is the fMRIB software library or Fossil, as it was determined to contain majority of the important tools needed for preprocessing. First, the input DTI and T1 weighted scans per subject are converted to a more software-compatible file format. Next, the DTI scan undergoes corrections for susceptibility-induced distortions, eddy current-induced distortions, and head motions, which are inevitable artifacts generated during MRI scanning. The corrected DTI is then used to estimate local diffusion patterns of the white matter tracks in preparation for probabilistic stratigraphy. We need to perform registration of the images between three spaces, namely standard space, diffusion space, and structural space, to output transform matrices that can warp brain parcellations from known brain atlases such as Schaefer and AAL, the subject structural space, which can then help in guiding probabilistic stratigraphy, which will recreate the map of white matter tracks of interest based on the parcellations. The final output is an RI by RI sized adjacency matrix, where each element is the structural connectivity probability between two RIs. Based on two parcellation schemes, the AAL 116 parcellations atlas and the Schaefer 7 networks 100 parcellations atlas, it was found that the DTI preprocessing pipeline can be assured to generate good quality structural connectivity matrices. This is important because we need to ensure that brain information is kept as intact as possible during multiple transforms during preprocessing that will impact downstream model analysis. With the generated brain graphs, we can perform graph-level binary classification using different GCN baselines. Different variations of model architectures were tested according to the diagram shown. We wanted to find out if hierarchical pooling will have an advantage over global pooling in the context of brain networks, and if the design of the hierarchical pooling layer such as diff pool, seg pool, and ASAP will affect classification performance. We also wanted to explore if the type of readout module, such as global pooling and learnable readouts, will affect classification performance. The PyTorch geometric library was used to implement model design, training, and testing. The dataset was roughly balanced, which included 41 subjects from the CN class and 38 subjects from the LMCI class. It was found that models trained on data parcellated from Schaefer generally outperformed models trained on AAL parcellated data, although the difference is not significant. Hierarchical pooling did improve test accuracy for Schaefer parcellated data, and in general, model architectures using diff pool yielded the best classification performance, followed by seg pool, then ASAP. Interestingly, global add pool was sufficient as a readout module for models to perform well. The record test accuracy was 96.25% for the model using diff pool and global mean pool trained on Schaefer parcellated data. More can be done to improve this project. This includes improving quality checks on the DTI preprocessing pipeline, using more parcellation schemes, stages of Alzheimer's disease, and other neuropsychiatric conditions for analysis, as well as adding an explainability layer to the model architecture to investigate which ROIs were retained after pooling. Thank you for watching.